Welcome to Chapter 9, Activity 3, where we're going to talk about means on dependent samples. So in the previous activity, we dealt with situations where the samples were independent, meaning there was no relationship between the data values from one set and the data values from another set. However, in real life, we sometimes run across situations where the data values are in fact linked. We call those dependent data, and because they come in matched pairs. And those could be such as before and after situations, left foot, right foot, or whatever the case may be. But there's a definite link between the data values, so we can't call them independent. So in this bonus activity here, I'll show you how we can handle those kind of situations where we have dependent samples. Okay, first off, we need to make sure that we're on the right page. So we want to check our requirements. So we want to check to make sure that the data is dependent. And I'm going to ask that you identify the link between corresponding data values. Okay. Number two, as always, we need a random sample. But since our data is paired, so a random sample of paired data. And finally, since we're dealing with quantitative data here, we need the number of pairs, which is n, to be greater than or equal to 30, or normally distributed. Okay. All right. So we can do hypothesis tests and confidence intervals for these matched pair data. And let's go ahead and do an example of a hypothesis test. Now, as you know, Professor Pedrero is not very tall, so you might get a kick out of this one. Is height a factor in whom you choose to marry? A random sample of 15 couples yielded the following height data in inches. Use a 5% level of significance to test the claim that generally the husband, H, is taller than the wife, W. Heights are normally distributed, and I got this data from StatCrunch. So first off, let's do our requirements. Is the data paired? And the answer is yes. Each one of these represents a marriage couple. Okay, so they are paired by marriage. Okay. Did we have a random sample? Yep. So we'll write random check. And now, were the number of pairs equal to greater than or equal to 30? The answer is no, but heights are in fact normally distributed. So we'll go with that. All right. So now we need to decide which population is which and then make a summary of our known information. It technically doesn't matter which one you choose for the sample 1 or sample 2. You'll end up with the exact same results in the end. So let's go ahead and just say that since husbands were listed first, we'll do sample 1 as height of husband. And I'll write that that was in inches. And then sample 2 will be height of wife. In inches. Okay. Now, we need to analyze our data. And since they came in matched pairs, what we're going to do is we're going to put sample 1 in list 1 and sample 2 in list 2. And then we're going to talk about the difference of these pairs. So let me give you a minute to type in that data and we'll do a quick pause. All right, so now I've got my data in the calculator. You can see the husband data in list 1 and the wife data in list 2. Since these are matched pair data, we need to do the next step, which is to find their difference. So the easiest way to do that is to come up to the L3 icon, make sure you're there, not just the first entry in L3, but the L3 icon, and let's type in list 1 minus list 2. So second 1 minus second 2. And what that will do is run a formula that says, hey, take 71.2 subtract 62.6, getting a difference of 8.6. So in this marriage, the husband is 8.6 inches taller than the wife. In the next marriage, the husband is almost a foot taller. In the third marriage, the husband is only 1.5 inches taller. Okay. Now, we're going to need some information from this third list that's the differences in the height. So let's quit out, go to stats, calculate one variable stats on list 3. Now, it tells me that the average is 5.24, but remember that list 3 was the differences in height between husband and wife. So what we're going to do is actually call this guy X bar D, in other words, the average difference in height. And so to 2 decimal places, that's 5.24 inches. And the standard deviation of the differences is going to be, to 2 decimal places, 2.97. Okay. All right. So we've got that. And now let's take and set up our hypotheses. Okay. Since we're going to be talking about match pair data, we're going to do not just mu, but mu sub d. In other words, the average difference. Okay. And our alternate hypothesis will be that the average difference is less than 0, the average difference is greater than 0, or the average difference is simply not equal to 0, so it could be higher or lower. And this will always depend on our problem. For our null hypothesis, we're going to conclude that the average difference is 0, so that there is no difference in height between husband and wife. Now, remember that our problem asked us to see if the husband was taller than his wife. And since husband was list 1 and wife was list 2, when we did L1 minus L2, if the husband minus the wife, if the husband is taller, then this should be a positive number. Okay, so the husband's height minus the wife's height, if the husband is taller, should be positive. Therefore, in our case, we're going to test that the average difference is greater than 0. Okay? And greater than is to the right on a number line, so this will be a right tail test. And we mentioned that this was going to be a 5% level of significance. So we now need to, let's try the traditional way. We'll need to find the critical value. And the critical value is n minus 1, where n is the number of pairs of data, which was 15. So n was 15 pairs. So degrees of freedom will be 14. And let's pull out our degrees of freedom table, the blue table. Here's our T table with the degrees of freedom down the left-hand side. And we had a 5% level of significance on a 1 right tail test. And so if we scroll down to 14 degrees of freedom, the critical value there would be 1.761. So 1.761. Let's go ahead and draw our picture here of our T distribution, which looks sort of like the Z distribution. He's just shorter and squattier. So our critical value, T sub C, would be 1.761. And that would give me 5% of the area to the right. Now, we need to find the test statistic. And the test statistic is found by this formula right here. And I'll show you something pretty cool here in a second. So we're going to do XD bar, the 5.25. We're going to divide that by S sub D, which was 2.97, divided by, notice how I use parentheses because we have an operation in the denominator, square root of n, where n was the number of pairs of data, which is 15. So our test statistic comes out as 6.83. Let's write that down to 2 decimal places. Okay. Oh, wow, I'm going to have to adjust my picture, aren't I? So if that's 3, 4, 5, 6, 7. So If we were to label our test statistic 6.83 on our picture, we notice that that lands way in the critical region. So we will reject H naught and conclude that there is enough evidence to conclude that, in general, the husband is taller than his wife. All right. Now notice that this doesn't preclude that some couples might have a husband who is shorter than the wife, but in general, on average, the husband tends to be taller than the wife. So we'll stop the video here so he's about 10 minutes, and then we'll pick up and talk to you about the p-value method on the next video.